Recording has started. So welcome. It is our great pleasure to have Tong Zhang here speaking at our seminar. He's a professor of computer science and mathematics at the Hong Kong University of Science and Technology. Previously, he was a professor at Rutgers University and worked at IBM, Yahoo, Baidu, and Tencent, and most recently Google. Tong Zhang's research interests include machine learning, algorithms and theory, statistical methods for big data and their applications. And he has many accolades, including that he's a fellow of ASA, IEEE, and IMS, and he has been in the editorial boards of leading machine learning journals and program committees of top machine learning conferences. He received his BA in mathematics and computer science from Cornell University and a PhD in computer science from Stanford University. And today, he's going to speak about feel-good Thompson sampling for contextual bandits and, in parentheses, reinforcement learning. Tong.
Okay, thank you, Shaba, for the introduction. It's a pleasure to give a talk here. So I have a parenthesis for the reinforced learning because I mostly will talk about the contextual bandits, but the technique could be applied to reinforcement learning. So that's why I just point out, but the main talk is contextual bandits. Okay, so basically there was this question. So for the Thompson sampling is definitely a pretty popular algorithm, both for bandits and also for the reinforced learning. One question is how to have some general analysis. There are analyses available, but for the particular problem, nonlinear contextual bandits, for example, they do not exist analysis before this. So one question is, can we use that to analyze? We'll come back to this problem later on. Also, if you use upper confidence bound for this analysis, that actually difficult to apply. So you have to get some other techniques, which I will explain in this talk. Basically, this is the work is try to starting from one question, nonlinear contextual bandits, whether you can have analysis for Thompson sampling. So as I mentioned, the previous analysis couldn't be applied. At least I don't know how to do that. So you have to come out with a new analysis. This is the main point of this work. Basically, one is using so-called decoupling, the other one plus the online regret analysis. So once you put that two pieces together, this basically shows you can do this. And you can simultaneously handle both Bayesian regret and the frequency regret in this manner. You can also handle infinite action space. And it can be applied to RL, as I mentioned, but I will focus on the bandits case, so you get the idea about essentially what this flavor of analysis is. Okay, anyway, so let's look at the contextual bandits. You have a repeated game between a player and adversary. So the player observe a context, which I will define by xt, which is coming from the adversary. And then the player picks an action, and then player receive a reward. I believe basically everybody in this talk probably familiar with, so I do not need to be elaborating on this. There are plenty of applications and also variations, more complicated form, but we are looking at the basic form, basically contextual bandits. So you observe X, take an action, observe reward, and so on. So notation, you have stochastic reward. Basically, R can be random, but it's conditioned on X and A, you can observe R. RT can change in principle from round to round, but essentially, it's not necessarily deterministic. And you have value function, which is what the more recent works on this problem focus on. And you assume you have a class of functions that actually can given X and A can find the expected reward. So this is your value function class. And then you are interested at each X, find the A which maximize your expected reward, basically of F star XA. And you observe a game history. I will just call the S. S is denotes a game history. Once you have S, you can find whatever your action. The regret is essentially taking expectation of what is the best possible F star X and what is F star of your action you put. So all these are standard. I hope this is essentially clear. There's nothing particularly new, but I just want to introduce the notation, the right notation, so that we can do further. And for the Thompson sampling, what happens is I start with approximation of my true value function. Let's say true function F star. I have function F theta XA. Theta is your model parameter. You want to find the model such that it's close to this F star. And once you have candidate model theta, you look at the greedy policy respect to your this function theta, the F theta XA. Basically, it's here. Essentially, when I take A with some theta and X, which means I will take argmax and assume this can be computed computationally efficiently. Basically, this one, either for finite action or for infinite action, assume there's oracle, which you can compute this efficiently. And then your model's value function once because your function is dependent on X and A, but once you plug in the greedy policy of your action of your model, then you get some function which only depend on X. Essentially, this is the value function which according to the best possible action of your model, as well as your model's answer to this. Basically, your model's answer to what is the best value you can get at X. So this one, essentially, we will use this notation. And the posterior sampling means that given the game history, I want to sample theta according to some kind of, this is a log likelihood, some kind of this and plus a prior over some theta. So this is a standard Thompson sampling. And you have this algorithm. Basically, I started from a posterior distribution. I will sample theta according to this posterior distribution, and I take a greedy action based on the theta I draw, and then this is basically my action. So I will draw posterior and then take the greedy action with respect to theta. Okay, I hope that these are all clear. Then distribution of A can be basically obtained by integrating out the theta, which this formula I will use, but essentially this one just say you have two ways to look at your distribution. You can either say that your ultimate goal is essentially distribution on A, right? So AT, because that's your policy. So this is essentially your policy. Given game history, given the current context, is your policy. The policy is they have a hidden variable theta, which is draw some function from your posterior, and then according to this theta, you take action. So you take action. So they send two steps, but in the end, you have you have a distribution on your action. So this is essentially what you get. Essentially, you can either say, okay, Thompson sampling is sampling the model parameter theta, or you can say sampling Thompson sampling. If you integrate out of the theta, you say I will give a distribution over A, a specific distribution over A. So that's just two different ways. Essentially, this sampling has some nice properties going from the theta to A versus you directly construct some A. I can say a little bit more once in the time, because there are the other algorithm is directly construct the distribution over A instead going through a theta of your value function. Okay, so so a natural and standard and is your negative log likelihood is least squares. Basically, that's a pretty. It assumes Gaussian noise, but in practice you can apply it for non-Gaussian noise as well. The question is, what is the regret of this problem? So that's what essentially I'm interested in. There are two types of regret for the analysis of Thompson sampling. A lot of work on the Thompson sampling use the so-called Bayesian regret, which basically say, okay, the Bayesian model is correct, and you also have a correct prior. Then, assuming that's the case, what is your regret when you draw the theta star from this particular prior? Frequency regress doesn't require the Bayesian model is true, doesn't require the prior is true. You just treat that as procedure. Then you say what is a worst case regret for any theta star belongs to some family. So there are two types of regret. So I would just say, actually, in this particular case, we can basically analyze pretty much similarly, very similar fashion. So a special case, what we are interested in following situation. So I just one thing I want to think is this one really is motivated by this paper. I think a lot of people probably know this paper. It's a pretty well-known paper. And there are some other follow-ups, but using similar structure technique. Basically, they say, okay, so you have a nonlinear contextual bandits. Let's say just simple case finite function family, just easier, but you can do that continuous as well. But let's just say I have a finite number of data. I have a finite number of action space. And I have a realizable condition means that there is a theta star which have this, but XA can be nonlinear. So there are work examples like linear bandits, like Shaba has worked on that, and a lot of other people has worked on that. But this one assumes this is a general nonlinear family. The question is, what is the desired you have regret? There were earlier work. But this work has this idea about reducing this problem into online regret analysis. And then you can show that this essentially is the bound you expect, the regret using. And this is a special structure of design some action directly based on, it's a different than sampling the action. So they have a randomized direct design of randomized action. So they using a different techniques, not Thompson sampling. I don't want to go over this paper. I think a lot of people against knowing this know this paper, but essentially Thompson sampling is different. And solving this problem, as far as I know, their approach is one, together with some variations. There are follow-up works, but mainly they all in the same flavor of this particular design of Dylan Foster and Sasha Rackley. So they are very similar to that. Thompson sampling, as far as I know, is a second approach, which is very different. And it also does the same job, basically. This is actually the question. So I'm trying to do motivation of that. Maybe because some background, part of motivation why I'm thinking about the Thompson sampling for this, because I look at this paper, I know this design. One thing I know, at least from earlier work, for the because they reduce essentially bandits to regret to the least squared regret. So essentially, I try to follow the same idea. So because this kind of exponential weighting, I know they can have a least squared regret. So that I know. Then is that possible? That's the question. So just natural to ask, is that possible to come out with analysis to say, this Thompson sampling can actually using similar ways to say reduce the bandits to least squared regret and come out. So this is a basic background of that. Actually, luckily enough, it's actually possible to do basically. So that's essentially this is the case. It's motivated this Thompson sampling analysis, and the end result to say actually it's possible to do analysis, but using a very different algorithm. But let's go back to the Thompson sampling. If I want to have a Thompson sampling to achieve that purpose, the question is the standard Thompson sampling okay? The answer is no. So that's why I have to come up with so-called a feel-good exploration term, which it's really optimistic. But I'll just give this example. Just say, okay, this is hopeless if you're just thinking about the standard Thompson sampling will do the work. So you have to make the modification. Consider there are two actions. You have theta 1 to theta n. Assume the 1 is the correct action. But for all j equals 2, correct action means you want to pull a equals 2, right? For every action else, you have a equals 1 is an optimal action for any other in your family, except the correct one. The correct one, you have 1 is your correct, but this one. What happens if you just use the standard Thompson sampling in this case? What happens is you're starting to pull randomly, and there's no way you always pull 1 because the algorithm always take the greedy policy. You have a very small probability you can pull this pull 2 only when you see the true see the star. But otherwise, you have a large probability you always see this suboptimal one. And but then you have a large probability of pulling that. You always never to explore action 2. So essentially, optimal is 2, but any optimal arm according to anything else is 1. So essentially, you have a high probability of pulling a equals 1. But then you cannot differentiate these two situations. You will never be able to do that. So essentially, to sum up, so you have a high probability of always picking a equals 1, and you have a flat posterior theta with that high probability. Therefore, you have a high probability pulling the wrong theta, and this high probability pulling the wrong theta allows you get a flat posterior. You'll never be able to find the correct to try to actually explore a equals 2 unless you pull O(n) times. And because of that, your O(n) times you have essentially constant times n instead of log n, and then you are not really doing so well. This one is a log n t. This one OT because you have to have O(n) instead of log n. So essentially, this bound you cannot possibly try to match the bound we want to with the standard Thompson sampling. This is why it has to be fixed that. So that's the main motivation to say, oh, I cannot do that with the standard Thompson sampling. I want to do something specifically in mind. And what is the fix? And the fix is you just adding a optimistic prior. The reason I didn't call it optimistic Thompson sampling, I realized that there is actually already taken by other people. So I have to change the name. So that's why I call it a feel-good exploration without optimistic. But essentially, this optimistic prior basically says I want to favor those theta with a larger reward. In this case, in the other example, I want to favor theta star because they try to show larger reward. Unless this can be proven wrong with a larger reward by least squares, I will always try to pull something favor is larger. So, and the main thing is to show that with this particular modification, it can address the exploration problem, and it can lead to the optimal frequencies regret. So this is essentially the work which is this. You have some roughly standard analysis, say bounded reward and the bounded function value, just for simplicity. What's new here is one is, as I explained, one has to add this feel-good prior. The other one is a new technique. The new technique is basically motivated by this beyond the UCB paper. which basically try to analyze the complex sampling by so-called decoupling. I will explain that. The decoupling will turn a partial observation problem, Bandits problem, into a least square regression problem. As I mentioned, for the Bayesian type of aggregation models, people know least square regression can be bounded. This is something I know before I do this, and that's why this technique is coming from directly motivated by I want to do this particular line of proof. So, okay, so this really is a reverse instead down. So essentially, yeah. So I think the new thing is really this decoupling. So because the other part, although you need to work out the details, but the idea is no, yeah, the least squares regression part. But how do you decouple? I will explain later. So unified analysis of Thompson sampling. So essentially, I will first start with a decomposition. Similar decomposition holds for reinforced learning, and this is how you can using similar approach. And actually, a lot of people use this type of decomposition in reinforced learning. So I use the same terminology here. One is this is a regret, which you start with this action you pull based on the theta you pull for the Thompson sampling. This is the highest regret you can possibly get. And it can be actually decomposed in this flavor. One is essentially what happens is you try to subtract at this is the point where your model pulls. So you want to subtract and plus this particular model value. So this one essentially is the model value at the action model pulls minus the true value at the action model pulls. This one is the optimal model value. This one equals this because this is a greedy action. Greedy action by definition, this equals that. But essentially, this one becomes optimal model value minus the optimal F star. So this is more like a feel-good term. This one is in the reinforcement literature, which we just reuse here. It's a Bellman arrow. So I just call it a Bellman arrow. So essentially, this decomposition. For the online, again, for the online bandits, this or reinforced learning, this kind of difference is very typical. So essentially, but then the idea is, okay, if I have this decomposition regret is this guy, I already say I need that. So I mostly want to care about this term. How do I want to analyze the Bellman arrow, which is the action you pull by your model minus the optimal, the true value. This is the true value what you will receive by this model. And we try to talk a little bit about this too, but this one I will talk about. But it's first I will first talk this one. So this is where actually the decoupling comes in, and that's the key. I would say this is probably the key contribution of this work. Basically, just observation. Decoupling itself is not too difficult to prove, but it's observation plus that together. With this type of technique, you can actually get the right regret bound. So that's so decoupling means I will assume. Let's say they have a finite action space. Left-hand side is basically Bellman arrow. So it's the at the action you pull by this model, and at the action you pull here. Okay, sorry, I think I have a little bit wrong. I think this one should be theta and this one instead of x and a decouple. I think okay, I will.
By the way.
Yeah.
Just for your information, if you're pointing with your cursor, no one can see it at the moment for some reason.
Oh, you cannot. Oh, okay, here.
Oh no, I can. Yeah, I can see if you're highlighting it.
Oh, okay. Then I need to highlight. Got you. Okay. Yeah. Okay then. So if I look at that, I think theta and a is coupled, which is where actually I mean mathematically what is because of this is partial information. You observe A only for this for what you pull instead of all other A's. And the decoupling means I cannot bound that using standard least squares analysis. I have to change this to be theta, not x and a. I think I wrote this wrong, but it's a theta and a theta, which are coupled, and this should be theta and a. This should be theta and a coupled. This is what happens with partial information. What I want in the right-hand side, and later we'll correct to the least squares. Here, what happens is theta and a are drawn from independent distributions. They all come from the posterior in some sense, but they are independent, conditional on x. So that's the key. Here, theta is drawing this guy. This a is, I'm always explained, a can be either thinking about as directly draw from a, or you can think about the given x as theta and a. So this a is, say, I would just draw in from the a, which is independent of this particular theta you draw. And this one is decoupled. Once you have that, you know that this one can be upper bounded by least squares. We'll go over that, but essentially, the idea about this decoupling to say, okay, how do I deal with Bellman arrow term? I will change the Bellman arrow, which this is a partial observation. Theta and a theta is coupled. I don't know how to bound that directly. Two, where I have least squares. So this linear becomes least squares. And then this theta and a now become independent. Once they become independent, it's like a full information distribution because you can always take expectation over A. You say, I observe all A by a certain probability, and then I can bound these least squares on the right-hand side. So basically, this, I think, is the main key observation of this work. I would say, if there's a key slide, if what one you want to take away, of course, you can say the least square analysis, but you know, as I may explain that it's appeared before, but this is one, as far as I know, it's novel. I'm not sure if other people use that before in some other contexts, but I personally didn't find it myself. So this one, I feel this is the main contribution, basically. And you can do that. The proof is not very difficult, so I'm not claiming it is difficult. It's just the observation. You do that. This one gets you the least squares, and then you that. So basically, yeah. So I will give the proof. Basically, after that, you say, okay, Bellman arrow, which is partial information. You get this on the right-hand side is a least squares arrow, which actually is a full information, because action is taken independent of your theta, and I can bound that using online regret analysis, right-hand side. Okay, and so the key is how do I make sure theta and a here are decoupled, and I will just show the proof. Yeah, this one just says online regret analysis can be bound that. But once you get this, you plug in the regret, you have another term of feel good from previous slides. So essentially, you have this term. We will talk about feel good later on, but essentially, you know, this square term. Now I get to bound this Bellman arrow. So let's explain this proof. It's very short, so it's not. I don't say it's a big deal. It's just the observation itself to be something. So basically, okay, this one is coupled again. So A is a theta xa. I just introduce indicator function with some a. Once I use the indicator function, this although it's coupled, it doesn't really matter. I will try to use Cauchy-Schwarz inequality. Here, I just doing that. This one is Cauchy-Schwarz from here to here. This one is just the equation. Just rewrite. There's a tuning parameter. You play around with the tuning parameter, and this is Cauchy-Schwarz. And then you get decoupled because this PA has nothing to do with theta anymore. Okay, this PA is just the probability of A already without independent of theta. So this is what you want. And through Cauchy-Schwarz, you just need to say what is this term. And this term I know has been used in other contexts like ESP4 analysis or whatever, similar things happens. But basically, you get something, sum over A. You get you get you get 1 over essentially I think essentially this one cancels. Basically this one 2 cancels, you get this one. So and then you just sum over A, you get a K. A belongs to this K number, you sum over K. So it's a quite a short analysis just using Cauchy-Schwarz to decouple this action and the theta, and then you get what you want. Okay. Once you get that, then we can go ahead. The key is it's not too difficult, but it's just a way to analyze this. Now we know that Bellman error can be reduced to least squares error for the analysis. So what about the feel-good terms? There are 2 things I want to say. One is for the Bayesian analysis. It is actually pretty well known in the Bayesian analysis. This has been used before. This inequality. Equality is an expectation of this feel-good term is 0. Okay. So then you can just use that for the Bayesian error analysis. For the Bayesian error analysis, you do not need to use this term because the expectation is 0. So you do not have that. Basically, you just say regret is smaller than least squares error. And you could use the standard Thompson sampling for Bayesian regret without using this feel-good term because the right-hand side is 0. So this term, okay? So then you can apply the Bayesian regret with the standard Thompson sampling. That's why people work with Bayesian regret with standard Thompson sampling, and it seems to work fine. For the frequentist, I don't know how to cancel this term, so I just keep it in the regret. Basically, essentially, this is just the same equation of that. Just rewrite a different notation. This is I treat this as a negative log likelihood. Basically, I will absorb this feel-good term into the definition of your negative log likelihood, and then I will directly say I can control the regret of this combined least squares and the feel-good term. So basically, that's what I actually do in the frequentist regret. Shava. Yeah.
Just a clarification question for all of this. So does this also mean that for the Bayesian regret, you wouldn't want to include the feel-good term?
That's I don't need to. I think it's always simpler not to need to
right,
include.
right,
so,
right, right.
Yeah.
And,
actually, you don't want to. You do not want to do that. Yeah. So that's true. Yeah.
And if you include it, what happens? You can still
if you
control
include
everything.
that, I think there is one problem of maybe one can reward a different way to. This one you have to manage. This one is for the standard Bayesian. Yeah. So you have to come out with something like this. Yeah.
Okay.
I believe it probably works maybe with a smaller equal or something, but one have to double check. I didn't check. Yeah.
Okay.
Yeah. Because this one is to say standard Thompson. This one Bayesian.
Yeah. I figured. Okay.
Right.
Good. Yeah. Thanks.
Yeah. Okay. So anyway, so this this is what you could always put that into regret. If you want, and essentially it can be managed. Okay, so this one. So let's look at the least squares term. This square you can rewrite. This is also fairly standard in this kind of analysis. Basically, least squares, original least squares is f minus f theta star. Maybe I will show you this. Yeah, I think I should have. This is a bit theta minus theta star square. You want to turn that into the observation R, right? So basically, it is well known if you have this, you get a difference of F minus RT minus F star minus RT. So it's just the sum of difference. And you can include that into your log likelihood because this one doesn't depend on theta, it always cancels. So eventually in the analysis, you include this. You basically say, this is your definition, and I will treat this guy, the difference as a log likelihood. And again, those analyses, although you work out a little bit difference in details, but those are quite similar to actually the other, like a hedge. This one very similar, and also there are some least squares. ESP4 using similar, but on the policy, directly on the policy A, instead using least squares regression. So this one is more regression based, but using same flavor of analysis. Here is a unifying analysis. Once you put that together, you have a regret smaller than this guy. This guy, if the Bayesian regret, lambda is 0. If it's not Bayesian regret, you put just a lambda. And this one is your least squares, we just mentioned. And this one you also minus the star. And so that's essentially you analyze. The main thing about this delta L is it can goes to 0 if you choose realizability, means theta equals theta star. At this point, this whole thing becomes 0. So essentially, you can see eventually when sample size becomes large, delta L is close to 0. That's essentially what how it makes this to work. Okay. So anyway, so this is essentially the equation we want to work with, and final analysis is coming to analyze this guy. And this guy is an online regret analysis, and this is coming from this type of analysis. As I'm explained, this flavor of analysis exists. You just work a slight difference in details. So your this particular L is least squares minus this feel good term. And then you take expectation of that. Basically, it's you take exponential. So I don't want to go to the detail. You can look at the paper or the reference. But basically, this is the kind of bound you get. So log partition function, this one, and is very typical in this online aggregation analysis. And plus lambda. And this one is usually is small. So this is almost 0 if you think about that in the case. And then this one is almost 0, right? You take expectation of this 1, log 1 is 0. So this one is kind of like 0. And then you have lambda square. Okay, so this is essentially what you get from the, you could also work out the Bayesian analysis. Actually, this is simpler because you have more control over the choice of eta. This one you can work on similar, but a little bit harder. I didn't do that in the paper. The paper only contains this one. You could do that. It's just a little bit more work. I don't see the point doing that, so I would just stop there. But this one is a little bit simpler, and you could because you choose smaller eta. So and once you have an eta, you can get this guy. Okay, you get roughly the same kind of equation, both for this Bayesian regret using standard Thompson sampling or frequency regret with a feel-good Thompson sampling. So yeah, here is what it gives you. Basically, this is a log partition function, and this is generally the claim of this particular result. And you optimize the lambda. So what you optimize the lambda is a kind of you balance these two terms, right? So basically, lambda is of the 1 over square root of t, of the 1 over square root of kt. Also, there's a partition function. Then you get this. So essentially, infinite actions, you could do that. So I think I will probably skip the infinite action, but I just explain that you could do that with infinite action case as well. Without difficulty. One thing I want to mention about infinite action for some of the work, for example, if you look at the other approach, like beyond UCB, this type of approach, if they work with the infinite action, they need to know this feature because they have to come out with a design. And also it's kind of complicated. I don't want to go to the detail, but they will work on that. For the Thompson sampling, you just need to know this exists. Algorithm itself doesn't depend on this at all. It just depends on F star, right? As long as this exists, it's fine. It doesn't mean you have to know this feature. So that's a little bit difference. And basically you get the same thing. So I don't want to go over. So, but let's look at the example. So what you get for this true value function, this is just some conditions. Maybe I will skip. Just say, okay, true function is small. There's an infinity norm boundedness of delta of two functions. But I think that delta is 0. I think probably for simplicity, we just look at the case of delta equals 0. And then this is, so delta can remove this, but basically this gets you the same bound by optimizing this condition. So let's look at the bound. Go back to the bound, maybe. Yeah, this is a lambda k. This is zt in the case of finite sample or finite class. It's a log n. It's basically log n. So you just balance in this two term, and this minus log n. So basically this minus zt is plus log n. You balance this two term, you get square root of kt log n. So this is basically here what you get by balancing this two term. We ignore this term, but essentially the point is to match this bound, which is the intention of the motivation of this work. And also it handle this one easier, more easily than what this can do. And the third one is alternative approach. It's very different from this approach, unlike the other follow-up of this work. Other follow-up, they are all very similar to this approach. It's just a modification on top of what this. But the Thompson sampling, which does the same job, is different. Okay, so this one is randomized over value functions. It's not directly sampling the A coming from the value function. So you first sample over value function, then taking the greedy policy over A. This type of approach, they always directly design some policy on A using a very specific design. Also, it's randomized. I believe one needs randomized for this problem. I don't believe determinism will work, but maybe, yeah. Some kind of randomization. Basically, I believe some kind of randomization is needed, some flavor. So both are randomized algorithms. This is randomized over A. This also randomized over A. And this one similar to ESP4. They are randomized directly over policy. This randomized over value function. So those are the difference. And when you wonder over value function, one good thing is it doesn't really care about the specific this feature representation, right? So if you randomize directly over policy, you have to know this feature representation. You have to work with specific this, but the other one doesn't. Anyway, so essentially for the parametric function, you can also get it's just slight generalization. You have a k dimension. You have a d dimension parameter. They can be not the same. You have a d can be larger than k or smaller than k, depending on the number of parameters, whether it's over parameterized or not. But basically, you can get this dkt. One is a dimension of a parameter. The other one is a dimension of the embedding space. So basically, you have you have this. Okay. So, this model is, I just want to say this model is tight because there are lower bounds to say you, 1D equals K, not K to the fourth. 4 is here. 4 is actually here. Okay. So D equals K. And then for the linear case, this is tight. So therefore, you cannot improve that. Comparison with ESP core, because I know some people may think, this is similar to ESP4. Reality is not. Reality, BIT4 is a policy. It's a pure policy method. You directly design policy. It's non-differentiable. And a lot of more recent work, even they started with policy, they ask they're differentiable. So it cannot. This one is not even policy gradient, right? So policy gradient, you can take a derivative with policy, but this one you cannot even do that. So it's very not implementable. As far as I know, I don't know how to implement it. I don't believe anybody would be able to. Thompson sampling is slightly different. It's more on value-based. It's a regression-based. Although you come out with this prior, I will show you just if you want to differentiate that, you can still differentiate. Basically, this is not differentiable. I don't know how one can actually, in practice, work with something like ESP4, while all the current value-based methods like value linear UCB or beyond UCB paper or this Thompson sampling, they all can be differentiated. They have value function based. And this one is just one say, okay, how to implement it? You just take gradient, and both can be gradient. The gradient of least squares is this gradient of feel good term is that. So both you can take gradient, and then you can say, okay, I will. One example, the implementation is SGLD. Then you just using this stochastic gradient type of flavor method to implement. So it's can be implementable. So that's a difference, and that's why people now a lot of people are interested in this differentiable and value-based systems. Okay, so in summary, so this problem is trying to address an open question motivated by this paper. And you have a unified theoretical framework for Thompson sampling, both for Bayesian regret and for frequency regret for nonlinear case. Thompson sampling, again, is the second method, as far as I know, to handle this problem, other than these were plus this variance. It has some variations which are similar. And what's new is you have to include that. I explained you cannot work with standard Thompson sampling. The proof technique, although can be used to handle both. So standard Thompson sampling or this in the Bayesian regret, or the frequency regret in the feel good. But the key is decoupling. Once you have a decoupling, you turn into a least squares problem, and then you know how to analyze by using taxes which know before. Essentially, you can handle different case. And I just quickly, again, I said that there's a term of reinforced learning. It's still possible. One way is there could be direct generalization. If you consider deterministic state dynamics, and then you that's also in the paper, just a flavor to show actually it works. And also you can looking at some other variations of that. It's possible to handle. Basically, it's possible to handle deep reinforced learning. Okay, using it. Anyway, thank you. So I think I'm on time. Yeah. Questions?
That's first class.
Yeah, this is wonderful. Thank you, Tom.
Thank you.
Yes. Yashin, I guess.
Yeah. So in the example that you showed that shows the regret bound of Thompson sampling, which is linear. So in that example, it looks like the problem is the choice of prior.
Right.
Because if you choose a different prior, Thompson sampling will have the optimal regret.
Yes, if you choose a different prior, if you favors optimistic, then yes. But then
I thought even in the normal prior. So if you show the example,
prior is I think it's uniform is a normal prior.
But I mean, you choose. I mean, this problem you can't just have a prior.
Let's go back to that. Yeah, let's go back. The normal prior won't work. Normal prior won't work because because you choose prior equal weights, right? That's the normal prior.
Sorry, but let's say if the prior is uniform over actions, like you disregard
the Thompson sampling
function
doesn't
class.
put prior on actions. They put prior on prior on theta. We are looking at a specific algorithm. If you put the prior on actions, then you have to come up with a different algorithm.
Or maybe you have to come up.
Algorithm, maybe that algorithm is more working with actions. Yeah.
Come up with a prior such that the prior induces a uniform distribution over the actions. That seems hairy.
I see what you're saying. I don't know. I mean, then what about the infinity actions? Then you have to really work very difficult to deal with that. Yeah. Maybe finite actions, you might be able to do that, but that's very challenging, I would say. Yeah.
Thank you.
Yeah. But this, I think, is a standard prior, the uniform prior. So, as far as I know, that's the most people probably would suggest in this kind of problem.
All right. So I actually do have many questions, but those are related to the parts where you went a little fast, maybe. So I don't know if you can like circle back to those.
Sure.
In particular, when you passed from this quadratic term to this log partition function, I sort of the part that I missed is okay. So why is this log partition function easier to work with? Why is
Hold on.
it
So,
easier to
this one is very typical in the Bayesian analysis and in the online regret analysis. In particular, for the finite action, finite family case, let's say you have an n number. This is just a log n. So you can always think that it's a generalization of this log n, but the log n is what you want. Yeah, it's an entropy of your log partition is like entropy of your, because yeah, in that case, 1 is 0, right? The other one, no matter how small it is, you have a 1 over n here, prior, and that particular point is 0. So you have 1 over n log 1 over n. Then you take minus sign, it's log n.
Right, I see.
Right.
So how do you connect this to the entropy? Sorry, I'm a little today,
yeah,
I guess like this is the conjugate of the entropy.
Yeah, it's kind of yeah. It's a little bit like that. If you think about this is 0 somehow, yeah, it's like posterior. Yeah. It's certainly related to other things. This shows up many other times. In fact, even the log determinant in the linear analysis can be interpreted as a partition number. If you integrate out this one in the linear case, it's a log determinant, which is shows up in the linear UCB analysis, other analysis. So they are the same thing, yeah, eventually.
All right, I see that. And I guess my other question was, in the concrete examples that you showed, how do you exactly bound this log partition function? I guess I missed something.
This example is finite, just for simplicity. Yeah, this is where this one gets logged.
Right.
Yeah.
Yeah, I was wondering if you skipped some other examples and details.
Oh, the other is I should say if you have a parametric. So let's say prior on this one is it's a compact set on a prior on some RD. Then log partition is a D. It's kind of a D log T or something, whatever. Yeah. Ignore the log T or something. It's just D. Yeah, it's actually D log epsilon or something like that. Right. So this is for the parametric case. Yeah.
Actually, can you explain this slide?
Yeah, this one is a little bit, it's more technical, but essentially what happens is you have a theta star. Your prior on that is not, it's relatively smooth. This one basically say with a very small, this one is unfortunate, but it's just technical. But essentially it's epsilon is, you get a very small ball. And then say prior doesn't change too much, that ball. This can be 1 over t, so it's very small, can be. Let's say 1 over t size or 1 over t squared, doesn't matter. As long as it's polynomial in t, it's okay, because this one comes to the log term. And then you think about volume of this is epsilon to the d, right? So volume. And volume turns into the log partition, because that's that is this guy doing that. And this is where this shows up, and this one is this volume within that small ball, and basically you have a prior, you have a log of this epsilon t is 1 over t or 1 over t squared, whatever polynomial in t. Yeah.
So if I have a compact set for the parameter vectors,
right,
and I put the uniform prior on it.
Yes.
What would be these quantities? Everything kind of works out, provided that...
I think it works out. There may be some depend on the diameter in this case.
Right,
yeah,
right.
I think
so
what I
just want to
gave
know that.
was, was there's also you could put a little bit Gaussian type of prior, but essentially, yeah, it's kind of work out. Yeah, basically this one
Let's
is
say
not.
everything is nice and bounded, like the radius is 1. Maybe we are on the
Oh,
unit
right.
ball.
That's fine. Yeah,
We are on the
then this
unit
one is
ball.
okay. Yeah, this one is not it's okay. Yeah, this one is okay. Yeah, it will be like that. Yeah.
And okay, so the epsilon t has to be tuned in such a way that the maximum loss that I can get over this ball is 1/t or something like that. That relates to the
Epsilon is because it's in the log. You have you have a tilde here. It goes into
right.
the tilde.
Right. Yeah. No. I'm just trying to parse of what you wrote here. So it's
Okay.
basically I have to choose the radius in such a way that over this ball, it doesn't matter what I choose and like what parameter we would choose. The difference between the true model and okay, so it's the difference between the true model and then approximate model over this ball is uniformly small.
Right.
And in the range of
And
1
the
over
volume
t.
is not too small.
1 over t, yeah.
Right. Yeah, I think this part can potentially be improved, but I didn't work out just using the simpler. I think a lot of RL paper have a similar flavor of using covering. This is like covering number.
Sure.
It's just the alternative of covering number. They all have a similar
sort of
thing. They didn't work very carefully. Yeah, as well. This one doesn't. It's not optimized.
So another thing that I was wondering about here is, I guess this also depends on the norm of theta and on the norm of W and the embedding.
Yes. Yeah, this all hidden into
this parametrization is.
I agree. Yeah.
W.
Yes.
Oh wait, no. Well, okay. There are 2 bullet points here. The first one is for the linear embeddable action space, and the second is like these are not the same, right? Like you don't need the linearly embeddable thing here.
Yeah, there are.
Like
one
for the
is
design,
right. One is exploration. So the linear embeddable, that is exploration. That is this K. Yeah, this is K. Yeah, K dimension. And the prior is for the covering number. So covering number is log n is a D. Yeah. In this case, it's a D. Yeah. D log epsilon, whatever. They are not the same, right? They are allowed to be different.
Yeah. Okay.
All right, very nice. So I have actually a more general question. I don't know if that qualifies as like a super technical question, but I was asking the same question to Dylan when he was presenting his paper in the seminar a while back.
Okay.
Which is what is exactly the role of the squared loss here, right? Because in their original paper they were using the squared loss, and here in this Thompson sampling work you're also using the squared loss, but it's only Thompson sampling if you squint a little bit, right? If you say, oh, we're using a Gaussian noise model.
I think it's here. If you can come out with something different for the decoupling for other laws, then you can use that loss, because the other one is a full information analysis. You can work with the different losses. But this one is, I think in their case, they have a different way of design that also depends on square loss. But this one, the decoupling in this one depends on square loss. But I believe you probably can do other laws. I don't know. I mean, it's when someone may need to come out. It's not it's not impossible. Yeah, I would say it's not impossible, but this is simple because this one is Cauchy-Schwarz. Yeah.
Right.
So basically, the key part of square loss use is here. Yeah. I think in their approach, it's a design of their action.
Yes, very cool. So here, you see this as Cauchy-Schwarz. I mean, of course, that's how it works. But I mean, I've been thinking about these algorithms myself quite a bit, and I see it as an instance of convex conjugacy, rather. That what you have here is like the conjugate of the square, and you decouple it into like a linear term and a squared term. And you can do that with other losses as well, not just the square.
Yeah, I think it's a little bit tricky because you have to have here you have to be bounded. It happens to work out for the square. It might be possible for other losses, as I mentioned, but one have to work out. Basically, one needs to. It's not. Basically, I would not say it's just completely straightforward, but one definitely need to work out.
No, it's definitely not trivial. It's beautiful. I love this.
Yeah, but basically, this is where actually it's square laws is. Of course, in the analysis also use square laws, but I would say that's probably not as essential in the log likelihood bounding these guys. Yeah, but this one definitely is more reliant on square laws. Yeah, at least in this analysis.
Yeah, I guess the squared loss is natural because you can really connect it easily with the likelihood. You can really relate the whole thing to Thompson sampling and posterior updates. Very, very cool. But I guess I don't know. I'm just wondering if there is like an inherent connection between Thompson sampling per se and the squared loss, or maybe if you change the loss around here to get something else that is no longer easily relatable to a likelihood, then you'd get another algorithm that's not Thompson sampling. I think this would be viable.
Yeah, that will be interesting. I don't know. I mean, personally, it happens, this particular analysis, I have thought about it. It seems to be pretty tied to the Thompson sampling in some way. This decoupling seems, I don't know how to apply this style analysis to some other algorithms. I personally don't know, but there could be a way. But because they all come from random, so you have a random set. I'm just interpreting this per se. This one is A, and then it's you have just this. This one is like sampling. Yeah, this one. So, but right. But if there may be possibility to, but definitely one have to change. One have to change things. Yeah. So to other. To come out with something else, but one never have to change. Yeah.
And I guess more along these lines, I don't know, maybe this is like the good time to go off the record, because I was going to ask you about this other follow-up paper by